Alright, so in this video, I'm going to be explaining another important article with the title A Broader Picture of Random Walk Based Graph Embedding. So, this KDD paper in 2021. Graph embedding based on random walk supports effective solutions for many graph-related downstream tasks. However, the abundance of embedding literature has made it increasingly difficult to compare existing methods and to identify opportunities to advance the state of the art. Meanwhile, existing work has left several fundamental questions, such as how embeddings capture different structural scales and how they should be applied for effective link prediction unanswered. So this paper addresses these challenges with an analytical framework for random walk-based graph embedding that consists of three components: a random walk process, a similarity function, and an embedding algorithm. Our framework not only categorizes many existing approaches, but naturally motivates new ones. With it, we illustrate novel ways to incorporate embeddings at multiple scales to improve downstream task performance. So, despite the rich literature, several fundamental questions about random walk-based graph embeddings still remain unanswered. Question 1. How do embeddings capture different structural scales? Random walks of different length are naturally associated with varying scales. However, downstream task performance of embedding has been shown to be insensitive to random walk length. Another relevant question is, how should random walk embeddings be used for link prediction? So with these questions in mind, we shall take a closer look at how embeddings are produced in random walk-based methods. It starts with selecting a random walk process. Deep walk applies standard walk, random walk, while no2vec considers biased random walk, and APP, for example, approximate personalized page rank. Page rank was originally in 1998, but there are hundreds of variations of personalized page rank. So it adopts rooted in page rank, among others. Then a similarity function maps realizations of random walk process into real values that represent some notions of node similarity. So this is the different random walk-based methods. For example, no2vec, we discussed no2vec APP. And deep walk is a standard approach. Deep walk, and it uses PMI, piecewise mutual information, is a standard. But although no2vec still is related to point-five mutual information, but it's a non-standard random walk. As I say, it's a biased. This is, for example, a biased random walk. And also, there are methods for factorization. So this is the transition probability proportional to the edge weight. For connected non-bipartite graph, the standard random walk is ergodic and has this stationary. If you solve it, you will see that the solution is this simple relationship. So it's the unique stationary distribution. When the Markov chains walks in these graph, suddenly it reaches until it reaches a stationary distribution that you see it doesn't change the distribution anymore, approximately, of course. And standard random walks provide natural way to capture node neighborhood. One can also design biased random walks to explore different, for example, node 2 vec that I will explain in part 97 is a biased random walk. Or for example, PageRank, which is originally developed by Google in 1999. And then so you need a similarity function, and we describe two random walk-based similarity functions: point-wise mutual information, which we call a PMI, and autocovariance. So for point-wise mutual information between two events, we can write it like this. For ergodic walk with stationary distribution as starting probabilities, PMI can be computed based on pi and a tau step transition probability. It is noteworthy that line and deep walk, two random walk embedding methods, implicitly factorize PMI. Autocovariance is defined as the covariance of x sub u and x sub v within a time interval tau. So for an ergodic walk and starting probability pi, we have this autocovariance. And you see in their appendix, they show you even the autocovariance for line method, DW. For example, here they prove that the point-wise mutual information, point-wise similarity, mutual information similarity matrix for the standard random walk can be expressed as this. And the embedding algorithm is what you need, because the goal is to generate vector representation that preserve a given similarity metric. So we want to design U such that it becomes as close as possible to these autocorrelations. And these similarities. But another paradigm is matrix factorization, which is an explicit way. You don't do it by computation. We just simply suddenly create matrix factorization. It generates a low-rank approximation, and it has a rich history in machine learning, SVD, and those things. But personally, I think these are not biologically inspired. Your brain doesn't create SVD approximation. Doesn't do anything like that. Everything is a process, simulation in your brain, just a message passing. So you should see if it is biologically inspired or not. But sampling-based methods produce embeddings that implicitly optimize equation 12 by maximizing likelihood of the corpus. A sample I is a random walk sequence of length L with initial node V sub 1 selected according to a distribution. So different from matrix factorization, this sampling algorithm produced two embedding matrices, U and V. The source and the target embeddings. The use of two embeddings was initially proposed in Dwor-2-Vec, as you know. It's considered a better alternative. We will focus on our discussion on algorithms that exploit negative sampling. Okay, so the form of conditional probability function is determined by the similarity function. For instance, in the case of PMI, it is known to take the form of sigmoid. So we define the conditional probability function. Rho is a piecewise linear activation. So, for a large enough dimensionality, the embedding that maximizes equation 13, this one, with a conditional probability is such that this holds. And the proof is the appendix of this paper. So their experiments is on these data sets. Cora is very easy data set. Wiki Fields, it has 10,000 nodes. Cora has only 2,000 nodes. Very simple. Block catalog has 10,000. Like Wiki Fields, 10,000. And so let's compare. You see the autocovariance and pointwise mutual information. So there are pros and cons on using them. And of course, as the x-axis is the training ratio. So as the training ratio increases, F1 score increases, but after that it is overfitting, which we try to avoid.